Hey everyone, and welcome. Today, we are tackling one of the most powerful, and let's be honest, one of the coolest topics in IGCSE mathematics, functions and graphs. We're going to take all those abstract formulas and turn them into a visual toolkit. Really, think of it like an architect's blueprint for understanding the world through math.
And that quote really just says it all, doesn't it? That's exactly what we're here to do. This whole explainer is about bridging that gap. Connecting the algebraic language you've been learning with its powerful visual meaning. By the end of this, I promise, you won't just be solving equations, you'll actually see them.
All right, so here's our blueprint for today. First, we'll get into why graphs are math's visual language. Then, we'll build up our toolkit with some core concepts you absolutely need to know. After that, we'll see calculus in action with turning points, apply it all to real-world rocket trajectory, and then wrap things up by answering some key exam questions. Sound good? Let's go. So, first things first, let's talk about why this topic is so incredibly important. I mean, this isn't just another chapter in a textbook, it's really the gateway to understanding much higher-level mathematics. This right here, this is where the magic happens. We're moving beyond just shuffling numbers and letters around on a page. We're actually starting to see the relationships they represent. Concepts like function notation and calculus. These are the powerful tools that let us translate that complicated algebra into a simple, understandable curve on a graph. Getting this down is, no joke, the absolute bedrock for A-level math and anything that comes after.
Okay, so we know why it's important. Now let's start building our mathematical toolkit. In this section, we're going to unpack the essential tools you'll need to analyze pretty much any function or graph that gets thrown at you.
First tool in the box, function notation. Now, it can look a little intimidating, but it's really just a very precise language. Think of a function like a machine. You put an input x into it, and the machine follows a set of rules to give you one single output y. And all those other notations, like fg of x or f inverse of x, they're just instructions for how to combine or reverse these machines. That's it.
Now, when it comes to straight lines, the rules for gradients are just beautifully simple. If two lines are parallel, well, their slopes are exactly the same. They're identical. But if they're perpendicular, making that perfect 90-degree angle, their gradients have this really neat trick. You multiply them together and they always equal -1. Simple, but super powerful.
And of course, it's not just about straight lines. You need to become a kind of shape spotter, able to instantly recognize the signature curves of these key functions. You see a U-shaped parabola, you should immediately think, that's a quadratic. You see that classic S-shaped curve? That's a cubic. Knowing these shapes by sight is a massive advantage because it gives you an instant feel for how a function behaves before you even calculate a single point.
Okay, toolkit's built. Now it's time to put these tools to work. We're moving into the really exciting stuff, using calculus to uncover the hidden secrets of a curve. This is where it gets fun.
So here's our challenge. We've got this cubic equation, and our job is to find its peaks and its troughs. The points where the graph just flattens out for a second before changing direction. Let's break down how to do it.
So how in the world do we find these points? Well, the key idea is that at the very top of a peak or the very bottom of a trough, the curve is flat for just a split second. That means its gradient is 0. So step 1, we differentiate the equation to get a new formula for the gradient. Step 2, we set that gradient formula to 0. Solving that gives us our two x coordinates, 2 and -1. And finally, we just plug those x values back into the original equation to find their y partners, which gives us our 2 points, 2, -15, and -1, 12. But which one is the peak and which one is the trough? To figure that out, we use something called the second derivative test. We just differentiate our gradient function one more time. Now, all we do is plug in our x values. For x equals 2, the result is positive. Positive means it's a minimum point. Think of a positive smile shape. For x equals -1, the result is negative, which means it's a maximum. Think of a negative frown shape. It's a fantastic tool that gives us the full story of the curve. That was some heavy abstract work, I know. But now for the really cool part. Let's take what we just did out of the textbook and launch it into the real world. We're going to use these exact same ideas to model the flight path of a rocket. Okay, here's the scenario. A rocket launches, and its height over time is described by this neat little quadratic equation. Our mission, should we choose to accept it, is to find the absolute peak of its journey. How high does this thing actually go? Right, here's the physics connection. For just a tiny instant at its maximum height, the rocket stops going up right before it starts coming down. Its velocity is 0. And since velocity is just the rate of change of height, we can find it by differentiating our height formula. We set that velocity to 0, solve for the time t, and it tells us the rocket hits its peak at exactly 3 seconds. Simple as that.
And now for the final step. We just take that time, 3 seconds, and plug it back into our original height equation. And the result? 45 meters. Calculus didn't just give us a rough idea, it allowed us to pinpoint the exact maximum altitude of that rocket. Now that is the power of applied math.
Okay, we have covered the core concepts and a really cool application. For our last section, let's nail down some of the most common questions and traps that pop up on exams. Think of this as our rapid-fire FAQ to get you totally prepared.
First up, this is a classic. It trips up so many students. The examiner asks you to sketch a graph, not plot one. So what do they actually want to see? What's the difference?
And the difference is absolutely crucial. Plotting is all about precision. You need a table of values, a grid, perfectly placed points. Sketching, on the other hand, is about showing you understand the graph's behavior. The examiner wants to see the right general shape and that you've clearly labeled the key features, where it crosses the axes, and of course, its turning points. Knowing this will save you so much time and grab you some easy marks.
Next question, you see dy dx written all over the calculus section of the paper, but what is it really? What does it actually mean?
Okay, if you remember one thing, make it this. You have to burn this into your brain. dy dx is the gradient. It's the formula for the slope of the curve at any single point. So the moment an exam question asks for the gradient or the rate of change, a light bulb should go off in your head and you should immediately think, differentiate, find dy dx.
And finally, let's clear up a common point of confusion: composite functions. When you see something like f of g of x, what's the right order to do things in? It is so easy to get tangled up here. The rule is actually really simple. You always work from the inside out. For f of g of x, you take the entire g of x function and you plug it into the f of x function wherever you see an x. It's like a set of Russian dolls. The g doll goes right inside the f doll. And please, please remember that the order matters. F of g of x is almost never the same thing as g of f of x.
So there we have it. We've gone from simple lines all the way to finding the peaks of complex curves, and even charting a rocket's flight. You now have the fundamental tools to visualize and analyze change. So the only real question left is, now that you can model a curve's path, what are you going to model next?
Thank you so much for watching! And for more helpful videos, math and science videos, don't forget to like this video and subscribe to our channel. See you soon!